Hi class, this lesson is on topic E3 and we are going to cover wave interference, media boundaries, and standing waves. So there are some interesting applications with this topic of waves, including noise cancellation headphones and musical instruments. So by the end of this lesson, I hope we can answer the following questions. What happens when two waves take up the same space or overlap? That's called interference. What happens when a wave reaches a boundary? So from one material to another, called media boundary. And what is a standing wave, and under what conditions will it be produced? So a standing wave is actually how a musical instrument works. If we have two separate waves taking up the same space, they can overlap. For example, if we have these two waves, notice that they are in phase, meaning that this one is not shifted compared to that one. The crests line up. When we play these two sounds together, we get this two sounds have the same frequency, which means pitch. If we add two sounds together with the same pitch, we just get a louder sound of the same pitch. So these nodes all line up, the crests all line up, the troughs all line up, but notice the amplitude has gotten bigger, both for the crest and the trough. On the other hand, if we have two waves that are taking up the same space and one is phase shifted compared to the other, the crest and the trough line up, we get cancellation of the wave. So these are two possibilities. These are the two extremes that could happen with interference, called constructive and destructive interference. And this is quite common that we will encounter a situation where two waves interfere with each other. So for example, if you have multiple speakers in one room, these waves interfere to create interesting patterns. They can be interesting, they can lead to many applications. In grade 12, we take measurements with interference patterns. So wave interference is actually a really important phenomena of waves, of mechanical waves. So when the waves add or overlap, there is the principle of superposition which applies. At any point, the amplitude of the two interfering waves is the sum of the individual amplitudes of the waves that make up that answer. So let's say if we have the blue wave and the green wave overlapping, there is addition of maybe 1 unit plus 1 unit giving us 2 units for the new amplitude. And if we have -1 here and -1 here, we have -2 there. So there's addition of amplitudes at all points of the individual waves to create the final wave. That addition happens as well with waves that are out of phase. So if we have the crest lining up with the trough, the +1 cancels out with the -1 and we get 0. Actually, at all points, whatever positive we have here cancels with the negative version of that number and cancels out. So -1 plus +1 is again 0. So this is how noise cancellation headphones work. And we'll talk more about applications. Okay, so for wave interference, the process of forming a wave with a larger amplitude when two or more waves combine. So let's say we have a crest going to the right and a crest going to the left. At the moment that there's interference, the amplitude is the sum of the individual amplitudes. And then after interference, the waves continue their original direction and are unaffected. So this crest with an amplitude of 1 that is moving to the right continues as an amplitude of 1 moving to the right after there is interference. But during the time of interference, the principle of superposition applies. And then there's also, okay, sorry, this is called, I can't see the heading here because of my recording view, but I'm assuming this is constructive wave interference. So that's when we get a larger amplitude, is constructive wave interference. Destructive wave interference is when we form a wave with a smaller amplitude than the two individual waves. before the interference. So let's say we have an amplitude of 2, this crest, this pulse going to the right, and an amplitude of -1 moving to the left. Well, at the moment that they interfere, we have the principle of superposition. +2 -1 gives us an overall amplitude of +1. So we get a smaller amplitude in the resultant wave. That's how we have destruction, because we had an amplitude of 2 and -1, and now we get a small amplitude. And then, just like with constructive wave interference, after the interference, the crest and the trough continue on in their original direction. So this crest with an amplitude of 2 that was going to the right continues going to the right with an amplitude of 2. Okay, so let's practice the principle of superposition. So the first tip that I have, this is a visualization activity. And sometimes the visualization comes very naturally to students, and sometimes it's a real struggle, or you don't know where to start. So I'm going to give you some concrete tips. So the first thing that I always do when I look at imagining this wave combined with this wave is I'm imagining, well, I identify if it's constructive or destructive interference. So this is a crest, it's a positive amplitudes, and this is negative. So when we add these two together, we are overall going to have destructive interference and an amplitude that is smaller. So I look at whether it's constructive or destructive, then I look at the width of each piece. So notice that they are the same width. That is good. So if I were to take a triangular size bite out of this rectangle, then I would be left with this piece. So that maybe is, if this comes naturally to you, that's enough. If you're really not sure what to do here, you're going to take the leftmost edge of one and add it to the leftmost edge of the other. So +2 minus -2 is 0. So I'm going to draw a horizontal line and I'm going to plot 0. Then on this edge, I've got +2 minus nothing. So I'm going to have a +2 on this side. So let me start drawing it out. So I have a dot here for 0 because 2 minus 2 is 0. And then I'm going to have over here, the answer is 2, or the sum is 2, because it's 2 plus 0 gives me 2. Now, you could find out a few different points in the middle. Maybe it's obvious that it's going to be linear, but I don't mind doing 2 minus 1.5 gives you 0.5, and then 2 minus 1 gives me 1, and then 2 minus 1/2 gives me 1.5. And then I connect those dots, and this is what my wave interference pattern will look like at the instant that they are over top of each other. Things get a little bit more complicated when the width of the crest and the width of the trough don't line up perfectly. So if I were to carry this square over to this triangle, there would be an edge of the triangle that does not get affected at all. But in the middle here, we're going to take this sort of a triangular, sort of like a house-shaped, upside-down house-shaped size bite out of this square cookie. We're going to actually end up with this. So we take the beginning, we put the triangle on top of the square, aligning the centers. So we can't just take the leftmost edge of one and add it to the leftmost edge of the other, because they are, one is 2 units width, one is 3 units width. So we're going to have to take the midpoint of the triangular piece, line it up with the square piece, and then right in the middle, you can say 2 units up minus 2 units down. So I know right in the middle, it is 0. Then if I'm 1 unit over, I have 2 units up from the square and sort of like a 1/2 unit down. So 1.5 is how high I would go on this side, and same with that one. And then hopefully you can see, based on that triangular shape, that it's linear. You take a ruler and that's that slope. But if it's not obvious, you can always take a point in the middle. So this is, the orange is 2 units high, and it is 1 and a bit units in the negative. So 2 minus 1 and a bit then you're going to plot that point here and here. Okay, and then you have these hanging edges where only the triangle is shown and there's no square taking away from the triangle. So that's our final answer of the second part of example 1. One more example. Now for the first two examples were destructive interference. We had a crest and a trough being added. So we had an amplitude that was smaller. We're going to take away from the amplitudes. Now you have constructive interference. So we're going to have a higher amplitude, and in the middle it's going to have an amplitude of 2, and then 1 unit to the left of that, it's going to slope down by 1 unit or a little bit more because this slopes down as well. Same thing on this side. And then we're going to see this piece and this piece. It's the hanging edges of that one. So we end up with this kind of like UFO looking spaceship shape. So the tips for these questions: identify whether it's constructive or destructive so you can start to try and visualize it. Identify if the widths match. If the widths don't match, you're going to imagine aligning one of the pulses on top of the other pulse with the middle points lining up. And so this would be the interference shape when they both line up. Okay, so applications of destructive interference, as I said, is the noise canceling headphones. So outside noise is detected and translated into some sort of a graph, and then noise is created on the inside of the headphones near the ear that is the same properties as the outside noise, except it's exactly out of phase. So we get noise cancellation because the crests line up with the troughs. Okay, now let's talk about what happens when a wave travels from one medium to another. Recall that sound is a mechanical wave, and all mechanical waves require a medium. And the medium properties are very important in determining the wave speed. And when a wave travels from one medium to another, let's take a look at what happens. So when a wave counters a lower density boundary, so going into, let's say, a flag, there's a wave through a flag, the material is the medium, so the fabric, into air. So the energy of that wave is going from material into air. This is a lower density material. The crest is going to hit that boundary and reflect back. There is going to be no inversion. So the crest remains a crest. It doesn't flip. And the amplitude is the same, and the properties don't change except for direction. On the other hand, when a wave encounters a higher density medium, so this is like a string that is tied on both sides, like as in a harp, when that crest reaches that boundary, it actually inverts. Reflection is inverted. Now, when a wave hits a wave hitting a boundary doesn't have to only reflect. When a wave hits a boundary, some of the energy can be transmitted or go through to the other medium, and some of it could be reflected. So this is what realistically, there are not many examples where there's 100% reflection. So let's say a wave is approaching a boundary and we're coming from a slower medium and going into a faster medium. And that's represented here by a really heavy rope, sending a pulse through a heavy rope, and it's approaching a knot between a heavy rope and a light rope. So that crest travels to the right towards the boundary. When it hits the boundary, some of that amplitude or some of that energy is reflected and some of it is transmitted. Notice that neither are inverted. So for slow to fast, there is no inversion. However, if we go from a light rope to a heavy rope, we actually get inversion of the reflected portion and no reflection of the transmitted portion. So from a faster medium to, from any faster medium to any slower medium, we get inversion of the reflection. Notice there's never inversion when the wave is transmitted. There's only the possibility of inversion when it's reflected. So there's a really helpful YouTube video. I cannot play someone else's YouTube video within my YouTube video, but I highly recommend this video that they do in like with glow in the dark sticks, so that you can really see that when this side, when this side is held fixed, there is inversion and the crest that is sent this way turns into a trough, but when it is not fixed, it comes back without inversion. So open, we can say open. So sometimes we say this is an open end or a faster medium. And sometimes we say this is a closed end or a fixed end going into a slower medium. Oops. Okay, let's not click on that. Oh yes, I can show you a simulation. So we're gonna show a water wave that is heading to the right. So let's go to the, and stop that. Let's stop sharing and go to the other window, Google Chrome. Okay. So we have a water wave, a linear water wave. So maybe this is a tank of water and we're looking at the top of the water and we drop a pencil that is creating a wave. If we were to bob that pencil up and down, creating a continuous linear wave, let's see what happens when this wave hits a barrier on the other side. So this is the leading edge, this is the crest, this is the trough. The crest is a dark color. And we see the inversion, it becomes a trough, the crest becomes a trough. And then if we actually continue watching it, there's actually this interesting pattern that forms as the original wave to the right is interfering with its own reflection to the left. Do you see how that pattern is creeping this way until the entire screen shows this is called a standing wave? And we're going to talk a little bit more about this. But this, I like this demonstration because it does show that when a wave hits a boundary, when it's a fixed boundary or a slower medium, the reflection is inverted. Okay, so let's take a look at this interesting thing called a standing wave. So draw your attention in this GIF or GIF to the blue wave. So just stare at the blue wave for a couple of seconds. Ask yourself, what is the direction of the blue wave? Okay, so the blue wave is from the left to the right. And when the blue wave gets to the end, it's reflected. And it becomes the red wave. So now stare at the red wave. Do you see how the red wave is going from the right to the left? Okay, now let's see, since these two waves, the red wave and the blue wave, occupy the same space at a point in time, the black wave is the sum of the red wave and the blue wave. So if you take a look at this black wave at all points, let's see when crest and crest line up. Do you see how the black wave is like, maybe it's double the amplitude? So when the black wave is at the top, amplitude red of 1, blue of 1 adds to amplitude 2. Now, just overall, let your eyes relax and look at that. The black wave have these red nodes. These are spots on the wave that actually look like they are not moving at all, and they aren't moving at all. So the blue wave is moving to the right, The red wave is moving to the left. What direction is the black wave moving in? So it appears that it's stationary. The particles are moving up and down, but there's no overall wave direction. So this is what a standing wave is. It's when an incoming wave is interfering with its own reflection, and the effect is it appears to be stationary. So let's open up a little simulation to take a closer look at it and see if we can create the standing wave. Okay, so in this simulation here, this is a string that is tied to this wall. And on this side, there is a motor to bob this side up and down. And we can set the frequency. Right now, I set the frequency to 6 hertz. And remember that that means 6 times per second. Now this is, I don't believe this is in real time, but we're setting it to 6 times per second. So as soon as, actually, oh, there's a little intro that I'd like to play. I hope it will allow me to play it.
Instruments emit sounds of particular frequencies because only these frequencies produce standing waves on the string or in the air column. Standing waves are waves that do not appear to travel along the string, although they are actually created by constructive interference between waves traveling both directions along the string. This simulation allows you to investigate the phenomena of standing waves. Be patient because the simulation builds up the standing waves gradually, allowing you to see how the standing wave is created from the reflections of the waves traveling along the string.
Okay, so let's press play on this 6 hertz wave. So right now, do you notice that by this bobbing up and down, we are going to send a crest towards this barrier. And remember, what happens at a media boundary when it is fixed or a slower medium? What happens to the wave? Is it reflected, or is it inverted or not? So hopefully you remember that it is inverted when it is a fixed end or a slower medium here. Do you see that? The crest turns into the trough. Okay, now I'm going to actually just let it play. And eventually we actually get this interesting wave. So originally we had a wave to the right, then we had the reflection to the left, and then the reflection was interfering with the incoming wave, and then we balance it out to have this standing wave. So notice there are these like 3 sections bordered by these nodes that don't appear to be moving at all. Okay, so that was cool that we could create a standing wave. Are there other frequencies that would work, or was that like a special frequency? So let's take it up to 14 and let's send a wave pulse down this side. So again, notice that this is a crest. Notice right there, the crest became a trough, so there was inversion. We have the incoming wave to the right, and we have the reflected wave to the left. Let's see if we wait long enough, if we can create a standing wave. And now we have a standing wave. It's similar to the other pattern that we saw in that it looks like it's standing still, and there are these nodes that don't look like they're moving at all. And then we have these spots where it looks like it's moving a lot. But there's a different number of sections. So we have 1, 2, 3, 4, 5, 6, 7. So we have a different number of sections, but it is a standing wave. So were those 2 numbers that I picked in particular? Yes, they were. So only certain frequencies are going to allow a standing wave to occur. If I switch it to 13 hertz, let's see if we can ever create a standing wave. Oh, something interesting happens, but no standing wave. So based on the length of this string, 13 hertz is not one of the frequencies that allow for a standing wave. So there is a special length to match a special frequency or range of frequency, a select number of frequencies that are multiples of something that will work to create a standing wave. So the multiples of 2 work for this string. So if I were to pick any multiple of 2, so 4, then I can get a standing wave eventually if I wait long enough. So I've got a standing wave. It only has 2 sections, but it's still a standing wave. Okay, so going back to our PowerPoint. So recall, a standing wave is an interference pattern produced when the incoming wave and reflected waves interfere with each other. The wave appears to be stationary. So among standing waves, there are different types of standing waves. We can form a standing wave where you have nodes on both sides if there are 2 fixed ends. So in the simulation, the rope was tied on both sides. This would be for any string instruments works this way. The frequency that you really hear when you strum a string is a frequency that works based on the particular length of the string. So if you imagine a harp, remember that harp strings have different lengths, and those different lengths give you different notes. We can also produce a standing wave if both ends are not fixed, if they're free ends. So this is, most brass instruments work like this. So instead of nodes, those spots that look like they're not moving, it's actually the antinodes. So the spots that look like they're moving a lot that have to go on the ends. So here we have nodes for fixed ends, antinodes for open ends. Sometimes they're called open ends, sometimes they're called free ends, but that means the same thing. So we've got fixed end, open end, or we can have open end, fixed end. So let's look at the anatomy of the standing wave, because I've started to use some terms that we haven't introduced yet. So notice that a node is located after every sort of like a lobe or a bubble. And then an antinode is an area where the maximum displacement occurs. So the node is the location where there is no motion, and the antinode is the location where there's the maximum motion. And that notice that the distance between a node and the next node is a half a wavelength. A fundamental frequency is the lowest frequency that can produce a standing wave in a given medium. And it's also called the first harmonic. Our harmonics are whole number multiples of fundamental frequency. So we can create a standing wave that's tied here and just has sort of like one lobe like that. We can create one that has 2 lobes like that. Or we can have one that has 3 lobes, or this one has 4 lobes. So there's, this would be the 4th harmonic of the string, because it's the 4th frequency that would produce a standing wave where there's a fixed end or a node, a node at one end and a node at the other end. Another way of saying that there's more than one frequency that works for a string of a certain length is by talking about the overtone. So that's a sound resulting from a string that vibrates with more than one frequency. So unfortunately, there's 2 different sets of language. We don't really need both sets, but since textbooks and resources go over both, I thought I would just highlight the difference. So for standing waves where we have fixed end on both sides, the lowest frequency that we can get with a node on one side and a node on another is like one of these lobes. And notice that this makes up half a wavelength. That's called the first harmonic, or the fundamental overtone. The next opportunity for a standing wave is when your frequency is such that it's one whole wavelength with the 3 nodes and these 2 lobe shapes. That's the second harmonic and the first overtone. Then the third frequency that allows a standing wave where it's fixed on both ends is like this, where you have these 3 lobes. And that's called the third harmonic because it's the third opportunity to create a standing wave. Or it's called the second overtone. And then the fourth one is when you have these 4 lobes. It's the fourth harmonic. It's the third overtone. So notice the overtone language is always one smaller than the harmonic language. And we don't say first overtone, we say, we don't say 0 overtone, we say fundamental overtone is the same as the first harmonic. And the first overtone is the same as the second harmonic. There is an equation that relates what fraction of a wavelength you have with the length of the string. So the length of the string, or the resonating length, is equal to a whole number times lambda divided by 2. So the whole number is called the harmonic number. So you have the first harmonic, second harmonic, third harmonic. This would be n equals 1, n equals 2, n equals 3. This is the resonating length, so that's the string in order to make that happen. And then we have the wavelength. Recall that in a set medium, the frequency, if V is set, V equals F lambda. So saying that you're changing the wavelength is the same as changing the frequency. So this has a higher frequency because the number of crest troughs is more frequent than this. So higher frequency, lower frequency. This is a larger wavelength. This is a smaller wavelength. Oops. Okay, so we've got resonating length. N is the harmonic number. Wavelength is lambda. It has to be in SI units. Actually, it doesn't have to be in SI units, but all the units have to match. And I think the easiest thing is to always report in the meters. Okay, now let's take a look at the open free ends. So to have open ends, you have to have an antinode on both sides. So up to here is the first harmonic. So this one that looks kind of like a sideways hourglass, that would be a first harmonic. Then the next opportunity is here. So that would be the second harmonic. And then this would be the third harmonic. So first harmonic, second harmonic. And we do have an equation for it. I should mention these equations are really useful and important, but what I would always do is always draw a diagram and then check to see if your diagram matches the equation. And I'll show you how to do that in examples. And instead of fixed, fixed, or open, open, we can have open and fixed. And this is the equation for it. So notice the equation for fixed, fixed was exactly the same as open, open. But when it's fixed on one end and open on the other, it is a different equation. It's 2n minus 1 over 4 lambda gives you the length. So this would be the first opportunity, the first harmonic would be from here to there. The second opportunity would be from there to there. Or actually, sorry, I've got this reverse. So starting here, let's say this is the bottom of your glass of water. So you have a glass of water and you're gonna allow sound to flow through it. This is the container of your glass and this is the surface of the water. So you have a fixed end here and open ends here. So that's one harmonic. Then the next opportunity, the next frequency where there will be a standing wave is this one. You have open and closed. And again, the equations are slightly different, but the equations are the same. The equations for the fixed end, the equation for the fixed end, free end, is different than the other two. So just when things are confusingly similar, but not quite the exact same, put them side by side so you can really establish what is the difference. So this one's divided by 4. This one's 2n minus 1 divided by 4. These ones are just n divided by 2. Okay, our first example, we have an open air column. So that implies that it's open at both ends. So we're looking at having an antinode on both ends of the column. And the length is 0.5 meters, so we have L. The air is 25 degrees Celsius. Calculate the frequency of the third harmonic. So you might wonder, why am I given temperature? But you might remember from last video that temperature tells you the speed of sound at that temperature. So we've got the speed. We've got length. What can we do with that? Well, drawing a diagram is always really important. It says that it's the third harmonic. So I'm going to draw an air column, and I'm going to draw the first harmonic, which would be that, and then the second harmonic, which would be that, and then the third harmonic, which would be that. So I've got, for the third harmonic, this is the diagram. And do you see how it's 1.5 wavelengths? So 1.5 wavelengths is 3/2 lambda. Notice that's the same answer you would get if you subbed into your equation. Ln equals n lambda over 2. It's the third harmonic, so L3 equals 3 lambda over 2. And if we know length equals 1.5 times lambda, and we know length, we can solve for lambda. Lambda equals length divided by 1.5, and we get 0.3333 meters for the wavelength. But we're asked for the frequency, not the wavelength. So we have to use our universal wave equation, V equals F lambda, to solve for frequency, and we do speed of sound divided by wavelength to get 1.0 times 10 to the 3 hertz. Okay, our next example. We have the sixth harmonic of a 65 centimeter guitar string, which is fixed at both ends, is heard. If the speed of sound in the string is 206 meters per second, what is the frequency of the standing wave? Uh-oh, how do I... Okay, there we go. So again, we're going to draw a diagram, and it said that it's a guitar string. That's fixed at both ends. So we're going to draw a node and another node. Actually, I have a trick for this. I don't end up, if I start with the nodes, then my lobe things or my nodes are not going to be nicely evenly spaced out. So I can eyeball this much better if I just start drawing frequencies and stop when I get the end number from the question. So it says sixth harmonic. So I'm going to draw the first one. That's the first. And then the second, and then the third, and then the fourth, and then the fifth, and then the sixth. And then I stop and I double check. Okay, fixed end is node at one side and node at the other. And I know n equals 6. I'm given that the length is 65 centimeters, which is 0.65 meters in SI units. We know the speed of sound in the string is 206 meters per second. So putting all of that together, our diagram or our equation will tell us that L is equal to 3 lambda. We can isolate for lambda to get 0.2167 meters. So again, that formula is n over 2 lambda. If we're subbing in 6, 6 over 2 is 3. We get our lambda, and we want to know the frequency. So we'll have to go to our V equals F lambda equation. Substitute in our values, and for frequency, you get 950 hertz. Okay, final question. 2.75 meter rope is fixed at one end and free at another end. Oh, did I give the temperature of the air? I think I have to give the, oh no, we're given the speed of sound. Okay, sorry. Here, we may have to assume the temperature in order to have the sound, the speed of sound. But we have length. It says fixed at one end, free at the other end. Draw a standing wave when n equals 3 and determine its frequency. Okay, so we're gonna draw where it's open at one side and fixed at the other. And if it is n equals 3, I will have 1, 2, 3. And then I can either use my diagram to see it's 1 1/4 wavelength, or I can use my equation. 2 times 3 minus 1 divided by 4 is equal to 1 1/4 lambda, or 5/4 lambda. And then to isolate for lambda, it is 2.75 meters divided by 1.25, and we get 2.2 meters. And then we have lambda, and we want to find, and we have V, we want to find F. Oh, why do we have V? We have V because we're gonna give you this number, 206 meters per second. I would either give you the temperature of the air in this example, or I would give you the speed of sound. So you do speed of sound divided by the wavelength that was calculated. Don't round it early. And for frequency, you get 93.6 hertz. I think it's 3 sig figs. N equals 3 is that's not a measured number, so we don't care about the significant figures there. But I see 3 sig figs in the other numbers. So 93.6 hertz is our final answer. Okay, so now it's time for you to do some practice questions. I've handpicked the ones that I feel are most important. So it is important that you do those to reinforce these concepts. Please make sure to hand in the exit ticket associated with this video as well on Google Classroom. And I hope you have a great day.